We discussed about histogram. In fact, we discussed about spatial filtering, and you saw that spatial filtering is a neighborhood processing, and it is going to take a decision based on some neighbor. So I can use a 3 cross 3 neighbor, or I can use a 5 cross 5 or 7 cross 7. So in the last class, I just demonstrated how, as I increase the size of this kernel, how low pass filter is going to, in fact, blur the image. The severity of the blurring increases. So we demonstrated it by using a MATLAB command also. Now let us move on. Let me just share my screen. Yeah, so this is where we were in the last class. Is the slide visible?
Yes, sir.
Okay.
Yes, sir.
So we discussed about smoothing spatial filter, and we saw how it would be useful in performing what is known as segmentation. When you are very particular about some part of the image to be recognized or identified as the foreground. If you have some noise like structure, then it's always better I smoothen it and then pass it through a thresholding technique so that I can get the required objects or recognize the required objects. So that is an application. Um, there is also another type of filter called order statistics filter, which is also a nonlinear filter. And I think I explained with an example how by using median we can remove what is known as impulse noise. A good example for impulse noise is salt and pepper noise. Okay, so there are also other types of order statistics filter called max and min filter. As the name itself says, once I do ordering in the median filter, I take the median. That means the middle one after I order. I hope you remember the. Okay, let me just open the OneNote also. So we actually used, in fact, a median filter of 3 cross 3 size, and you saw that any pixel like uh, 255 or 0, obviously, because once I arrange them in an increasing order, is the OneNote visible?
Yes, sir.
So
Yes, sir.
once I order them in an increasing order, obviously, a very low value like 0 or a very high value like 255 will be in the edge. So low value will go to the left side and high value will be at the rightmost position. So when I take a median, that means the middle point of that, obviously that I will be removing these two. That means that is how it has happened. You can see that 255 is replaced by 14, 0 is replaced by 12 here. So uh, this can remove salt and pepper type of noise. Now suppose if I do the same operation, that means I just arrange them in an increasing order. Instead of taking the median, if I take the maximum value of it, or if I take the minimum value of it, then that becomes a max filter or a min filter. For example, in this case, assume that I just use a min filter here. Okay, in this case, I'll use a min filter. So that means I'll take the minimum value, which means that 0 will be taken and 0 will be replacing here. If I take in this case say a max filter, then it will take 255 and replaces it. So that is the difference. Now, can anybody tell me which type of noise can be removed by using max filter? Any guess? If I use a max filter, I am guaranteed that a particular type of noise will be removed. What is that noise? Any quick answer? Okay, I'll also give you an option. Will it remove the salt noise or pepper noise? If I use a max filter, will that remove salt noise or pepper noise? I'm not putting both of them together. Assume that I have an image with salt noise, assume that I have an image with pepper noise. Salt noise means white pixels, pepper noise means black pixels. So which, yeah, I think somebody is answering through chat window. Pepper noise. I think it's yeah,
Paper
pepper
noise.
noise. Yeah, Sindhu is answering. Okay, fine. So when I use max filter, obviously I'll be taking the maximum value. So I am sure that the minimum value is removed, which means that it is going to remove pepper noise. So max filter can be used for removing pepper noise, and obviously min filter can be used to remove salt noise, because when I take the minimum, higher values will be removed. So it is, so when I have an image which has got only salt or noise or only pepper noise, I can use these type of filters, max and min filter. Okay, thanks for that answer. Fine. Okay, so I think there are examples here which I have already shown you. This is an X-ray image of a circuit board which is corrupted with salt and pepper type of noise. I hope you can notice white and black dots here. Now, if I use a simple averaging filter, it actually spoils the image rather than improving it, because obviously averaging filter is going to smear the values. Whereas if I use a median filter, it can remove, as you can see. So it has removed most of it. And suppose if a median filter has not removed all the salt and pepper type of noise, it is allowed to even apply a median filter more than once. Okay, so instead of applying once, you can apply twice. But it is not advisable to apply it more than twice. That means if I keep applying the median filter more than 2 times or 3 times, that means if you increase the number of times I am applying median filter on the same image, first one or two iterations it will remove salt and pepper noise, but later what happens is it will also start removing the edge information, obviously, because it also starts seeing the edges as the noise. So it is not wise or advisable to apply median filter too many times. Okay, once is better. If there is still some noise, you can apply it one more time on the same image, but don't do it more than that. So what I suggest is just run by using maybe my online MATLAB, or if you have MATLAB on your laptop, apply a median filter on an image. Yeah, okay, I can also give you the command MEDFILT2, midfilt2. Okay, so that is the command. Maybe on the chat window, I can just give you that command. So this is the command for applying a median filter of dimension 2 dimension. So midfilt2 on an image. You can even specify what would be the size of your kernel as 3 cross 3 or 5 cross 5. So what I suggest is read an image, add salt and pepper noise to it. IM noise is the command to add noise. Okay, please look for these commands and try to do it. So add noise, remove noise by using the median filter once, apply it twice, keep applying it more than 2 times, and start seeing the in fact the adverse effect on the image. Okay, so let us move on. So previous category of filters are called smoothing filters, because they are low pass filters. They are trying to remove the edges, but that means smoothen the edges. In the in fact effort to smoothen the edges, it has also smoothened noise. I hope you remember this example. So this is a noisy area. So as I increase the size of my smoothness filter, you could see that the noise is completely removed, but that is at the cost of removing edges. So when you are applying low pass filter, you have to be very careful. You cannot increase the size of the kernel too much, because you will be losing the image features also along with the noise. Okay. So the opposite to that is a high pass filter. Okay. Now I am interested in finding the edge information in this case. Okay, so that means I should only pass edges and remove the smooth region. High pass filter does that. It increases, sorry, it allows the high frequency components. That means edge information is allowed, but it will in fact remove the low frequency region. Okay. In this case, if you have carefully observed, what you did is you just added all the pixels, okay, and then averaged it. Okay, so this is a sum operation. So obviously, you know that if a sum operation can perform low pass filtering, a difference operation will perform high pass filtering. So uh, we use a differentiation operation, that means a derivative operator. Okay, integration or summation performs low pass filtering, so definitely derivation or differencing will perform high pass filtering. So let us try to understand this derivative operation. Suppose if I want to take a partial derivative along x direction, we'll take one dimensional first. How do I do it? I have to use a difference operation. So you can see that I'll take f of x plus 1 the value, subtract f of x. So the difference operation. F of x is the current sample, f of x plus is the next sample. So I just take a difference of those two. This is the first derivative. But usually they use second derivative. So second derivative means, carefully observe, I'll take f of x plus 1, add it to f of x minus 1, that is the two neighbors, and subtract 2 times f of x. So what actually you are trying to do is, you are trying to subtract f of x plus f of x from f of x plus 1 once, and f of x from f of x minus 1 once. That means I am applying the difference operation or the derivative operation twice. That is why it is called a second order derivative. This is for a one dimensional signal. So I can even show this on a simple example of 1D. Let me just close the video. Okay, so I'll just take a one dimensional signal. Is the one note visible?
Yes, sir.
Okay, I'll just take this type of signal. One dimensional, first order derivative means I have to take f of x plus 1 and subtract f of x. That means this is what I have to do. So 10 minus of 10 is 0. Then 10 minus of 10 is 0. 100 minus of 10 is 90. 100 minus of 100 is 0. 100 minus of 100 is 0. Actually, there is nothing here, so let us not worry about this. Okay, so border is neglected. This is a first order derivative. If I take a second order derivative, the formula that I have to use is this: f of x plus 1 plus f of x minus 1 minus 2 times f of x. So let us not worry about this. So we will go here. Okay. So 2 times of this is 20. So 10 plus 10 is 20. So 20 minus 20 is actually 0. I hope you understood. So this is f of x. So 2 times of that is 20. Plus this plus this. So 10 plus 10, 20 minus 20 is 0. So this would be 0. So in fact, how it can be done is, I can apply another stage of first order derivative on this itself. Okay, so you will get back the same answer actually. Anyway, let us not worry about it. Now let me go to this case. So 2 times of that is 20. So 110 minus 20 is 90. Is that correct? 2 times of this is 20. 100 plus 10, 110 minus 20 is 90. Now if I go here, 2 times of this is 200. So 110 minus 200 is minus 90. If I am here, 2 times of 100 is 200. 100 plus 100 is 200. So 200 minus 200 is 0. Let us not worry about this. Okay. In fact, you could have done this by directly taking one more step of derivative on this. Okay, so 0 minus 0 is 0, 90 minus 0 is 90, 0 minus 90 is minus 90, 0 minus 0 is 0. Did you understand the procedure? Hello?
Yes, sir.
Okay,
Yes,
so first, this is the first order derivative, this is the second order derivative. Notice what has happened. What is important is this. You observe this portion of the image, signal. There is a sudden change from 10 to 100. Okay, the value is changing from 10 to 100. So, you know, if you see this as an image, this is an edge in an image. This is an edge in an image. And whenever I have an edge in an image, okay, you could see that you will get a non-zero value in the first order derivative. But whenever I have smooth region, for example, 100 100 they are all smooth regions, 10 and 10 they are all smooth regions. So you know, a high pass filter, whenever there is a smooth region, it will not allow those low frequency components, so you are getting zero. So the response of a first order derivative is it only gives a non-zero value whenever there is an edge. Okay, now look at the second derivative. Here also you can see that whenever they are smooth, it is 0. But near the edge, what you will see is you will see a variation from 90 to minus 90. 90 to minus 90 means it is actually, in fact, 2 times this 90. So what is happening here is um, you are getting, this is actually called double edge effect. We will take a typical example in the slide and see this anyway. This is called double edge effect. So whenever there is an edge in the image, I actually see a double edge here. So this is an advantage because you clearly extract edge information from an image when I apply second order derivative. Okay, so let us move on. Sorry. Okay, so is the slide visible?
Yes,
Hello?
sir.
Okay,
yes, sir.
okay. Yeah, so let us take an example and see what is the difference between first order derivative and second order derivative. In fact, I have already shown one difference. So first order derivative has got some characteristics, second order derivative has slightly a different characteristic. Let us see. So the example that is taken here is this image. This is actually a small image, and what is done is a 1D horizontal line is taken, and in fact it is taken exactly at this point. Okay, exactly at this point it is taken. Do you notice some white dot here? Is it visible on your screen in this place?
Yes,
Yes,
sir.
Okay, okay, so that's what is important. So on this line, if I just move, what you observe here is, you can observe here, the value is white here, so you could see some high value here, and as I move the value is decreasing. You could observe the decreasing in the value, and then it has become dark. It has become dark, and then at this point suddenly the value has increased and it has come back. Okay, that is this white dot. Then when you go here, you see a small ramp type of it that you see here. And when I reach here, suddenly the value is going from black to white. So you could see that. I hope you can understand this horizontal line which was taken exactly at this point. So this is that 1D array or 1D data at this particular point. So what you should notice is there is a ramp here. We call this as a ramp edge. Now there is actually an isolated point because why it is called isolated, because the neighboring values are different whereas this value is very high. So we call it as an isolated point. We can also call it as noise. So there is an isolated point, and there is what is known as a triangular type of it. That means the value increases and then it has decreased. Value increases and decreases, and there is a sharp edge here. So you have a step edge, you have an isolated point, you have a triangular type of edge, you have a ramp edge. Now let us see how first order and second order derivative operates on this and what is the observation. Okay, now just to uh, in fact take difference operation, you have to actually sample this. So the sample data is given here. Okay, so this value is 5, then the ramp edge, it is increasing from, sorry, decreasing from 5 to 4, 4 to 3, 3 to 2, 2 to 1 and 0. Then it is 0, all of them are zeros as you can see. Then suddenly it goes to 6 and comes back. So this is an isolated point. Then it is 0 here. Then you have a ramp, sorry, a triangular edge here. It is going to 1, 1 to 3, then 3 to 1 back and 0. So this is a triangle. Then there is a step edge here. From 0 it is going to 7. So this is a step edge, this is a triangular type of edge, this is a ramp type of edge, and this is an isolated point. So the values are shown here. Okay, all the values are printed here. Now first order derivative, when I am here, what you do, 4 minus 5 is minus 1, 3 minus 4 is minus 1, 2 minus 3 is minus 1, 1 minus 2 is minus 1, etc. 6 minus 0 is 6, 0 minus 6 is minus 6, again 0 here, and so on and so forth. I think it's not difficult for you to take the next value, subtract the present value and write this. Okay. Now when I come to the second derivative, as you know, you have to again take one more derivative on this. Either I can use this or I can directly take this. If I use this, I should use the formula, this formula, second formula. If I am doing it on this, you just do one more first derivative on this. Okay, so observe here, minus 1 minus of 0 is minus 1, minus 1 minus of 1 is minus 0, minus 1 minus of minus 1 is 0, etc. Okay, so I hope this is not a difficult thing. For example, here minus 6 minus of 6 is minus 12, 0 minus of 6 is plus 6. Okay, is this clear how this is written? A simple operation. Any doubt? Somebody respond. Okay, so this is a very important concept. Please don't hesitate to ask any doubt or anything. So I'll repeat what we are trying to do. We are trying to see the effect of first order and second order derivative on different types of image details. A ramp edge is there, an isolated point is there, a thin fine line, what we call as a triangular type of edge is there, a step edge is there. So with this is the observation. Now what are the observation? I have listed all of them here. Let us take one by one and just compare the results. First order, it is non-zero along the ramp. Look at the ramp. This is a ramp. Wherever it is a ramp, you know it is non-zero. The values are non-zero. Okay. So during the ramp, the values are non-zero. That is the first observation. Now second order, non-zero only at the onset and end of the ramp. Observe the same thing in second order. This is a ramp. See, when the ramp has started here, it is non-zero. When the ramp has ended here, it is non-zero. Do you notice that? When the ramp has started, it is non-zero. When the ramp has ended, it is non-zero. Whereas along the ramp, the value is 0. That is the first difference. First order derivative has got non-zero value along the ramp, whereas the second order derivative has got non-zero value only at the onset and end of the ramp. But during the ramp, its value is equal to 0. That is the first observation. First order produces thick edges and second order produces finer ones. So you can clearly observe here. See, this is an edge actually, and what you see, all these are non-zero values. So I actually get a thick edge here when compared to the second order. So that is the second observation. First order produces thick edges, whereas the second order produces finer ones. Another important thing is response at and around noise point is much stronger in second order. What is that noise point? This isolated point. I told you this isolated point is noise here because The entire other region is smoother, whereas here suddenly it is going to 255. So when I apply a second order derivative on this, what will happen? Just observe. In this case, just see the value is changing from 6 to minus 6, minus 6 to 0. Okay. So you can just observe the change is only minus 6 here. Now observe the same thing in the second order derivative. The value is changing from 6 to minus 12 and minus 12 back to 6. So the change is too much here. 6, it is going to minus 12. Again from minus 12 it is coming back to 6. So that's exactly what I have written here. So the response at and around noise point is much stronger. What does it mean? When there is a noisy image, if I am trying to find edge information from that, second order filter is going to actually spoil because it is going to enhance the noise. Okay, that is a disadvantage of second order filter. However, second order filter produces finer edges when compared to first order filter. So if it is noise free image, second order filter is very good. If it is noisy image, you should first remove that noise and then apply a second order filter. Otherwise, second order filter is going to in fact give a high response or strong response near the noise point. And there is also what is known as a double edge effect in second order. Okay, this is the double edge effect. I think I have already explained what is it mean. For example, look at this, or in anyway, for example, here you see the value is going from 0 to 7 and 7 to 0, whereas here it is going from 0 to 7, 7 to minus 7. So there is a positive value, there is a negative value. This effect is called double edge effect. Okay, so these are the various observations, and after looking at all of them, usually second order derivative is used because it enhances finer details in an image. But only thing is you should take care of noise. That means you should first apply some noise filtering technique and then use a second order filter. Okay, so what I explained here is for one dimension, but we have to do it for two dimension. Now if it is for two dimension, you do the differentiation both along x direction and along y direction, and of course here we are doing second order differentiation. Once do it along x direction, second time do it along y direction, and then add them, you will get the difference image. Okay, so this is a second order derivative in the x direction, this is a second order derivative in the y direction. Add both of them, I'll get the difference, and this operation is called Laplacian operation. Please remember this. This operation is called Laplacian operation. Okay, so this is Laplacian. That means taking second order derivative along x direction and y direction and adding them. Now this is differentiation operation, but image is a digital image, therefore I have to apply difference operation. So let us just now use this formula, except that now I also have one more variable y, so I have to be very careful. So along x direction means y will not change, you know that. So you can observe here only x is changing, f of x plus 1 y plus f of x minus 1 y minus 2 times f of x. So this is the original, this is the center pixel value, this is 1 to the right, this is 1 to the left. So you have to just take the difference of those things. Okay, and then add them. Again along y direction, you observe here x is not changing, x is remaining same, only y has changed, y plus 1, y minus 1 and y here. Okay, so if I add both of them, I will get the Laplacian like this: x plus 1 y, x minus 1 y, x y plus 1, x y minus 1, and the center value is f of x comma y. So you can observe that the center pixel is multiplied by minus 4. These are the four neighbors of an image, all of you know about it. So the four neighbors are multiplied with plus 1. So if I show this as a kernel, this is how it looks. Look at the first kernel, don't look at the others. Look at the first kernel. So the center pixel is minus 4. These values are 1, 1, 1, 1, and I am not doing anything with these, therefore they are 0. Okay. So this is the equation and this is the kernel. Minus 4, 1, 1, 1, 1, and these are 0, 0, 0, 0. So if I apply this type of filter, it is going to detect edge information from the image. Now you may ask me a question. You have taken along x direction, you have taken along y direction and added. Now the question is, will there not be any change along the diagonal directions? The answer is yes, there will be changes along the diagonal direction also. So if you introduce the diagonal direction also into the consideration, I can modify the kernel like this. Okay. So I just make all these diagonal values as 1, and the center one which should be -8. So I will be taking even the diagonal direction also. Okay. Another question is, in this formula, I have taken this as minus, this as plus. Whether I take the difference like this or I take the difference like this, finally you are going to get the edge information. So I can make this plus and make these two minus. So which means this will become plus and these four will become minus. So I can use even this kernel also. Center value plus 4 and the 4 neighbors as -1. Of course, if I introduce a diagonal neighbor, center value is +8 and all the neighbors as -1. Okay. So these are the 4 different filter masks that are used. Normally, we will be using this or this, not these two, because this is taking care of the diagonal edges also. Okay. So, but this is actually the Laplacian, which is taken only along x and y direction. Okay. Now notice one more thing here. I think I'll compare that with your, okay. Here I told that the weight of these is equal to 1. For example, 1 by 9 added 9 times, I'll get 1. All these added, I'll get 16. 16 by 16 is 1. Why this characteristic? Because this is a low pass filter. When I apply this image, this kernel on a smooth region, it should not do anything because it should allow it as it is. That is why the sum is 1. Whereas in the case of high pass filter, when I apply it on a smooth region, what will I expect? What will I expect when I apply this on a smooth image or when the a smooth region? What should I expect? Can somebody comment? This is a high pass filter. Smooth region means it is low frequency region. Should it allow or should it block? Anybody?
Blocks.
It should block, right? Correct?
Yes.
Okay, so since it has to block, what does it mean? Whenever I have a smooth region, I should get 0 as the response. That is why if you just look at the weight, total weight, it is equal to 0. 8 and these are -8, so the sum is 0. -4 plus 4, the sum is 0. So this is in fact one of the necessary condition for considering a filter to be a low pass filter or a high pass filter. So in a high pass filter, the total weight is equal to 0. In a low pass filter, the total weight will be equal to 1 because it has to allow the smooth region. Okay. So I think the results are very clearly seen. I am avoiding MATLAB demonstration just to save time because we are running, in fact, going very slow with respect to the lesson plan. So let us avoid it. Hopefully, with the exposure that you have so far, those of you are interested can go further and try to simulate these type of uh, techniques. So this is an image of north pole of the moon. What is done here is Laplacian filtered image. Okay. Do you see these edges here? This, there is a sharp edge
Yes.
here, that is this region. Not only that, even within the moon region also you could see that there is some edge information. Just to see it better, what is done here is actually you are just adding you are just scaling this by some value. So Laplacian image is scaled for display purpose. That means I just multiply this by some value and display it. So you could see the edges and also the small edges that you see here. Okay, fine. Now, how do we use this information? How do we use this information is, for example, if I'm working on maybe say license plate region recognition of an image, or license plate recognition, because of some blurring, the edges of the license plate number may be not that good. So is there any way I can enhance this edge information or crispen these edges? That means I'll make the edges sharper. Okay. So what they do is, they will just take an image like this and apply a Laplacian on this, so they will get the edge information. Now if I take this image and add it back to the Laplacian, please understand the step. I will take an image, take the Laplacian on this, and then add this Laplacian to the original image. So what happens is, wherever the image is smooth, nothing, the value is 0 here, so nothing will change. So the smooth region remains as it is. But wherever there is an edge here, since I have that edge detected here, when I add it back, only that edge information gets crispened or enhanced. Now please notice this image. I don't know on your computers or laptop or the mobile screen whether it is very visible to you. You should be seeing this edge much crisper or sharper compared to this image. If at least one of you say yes, I'll be happy. Okay, this portion is very clear here in this case. And not only that, look at this region and also look at this region. Do you see the small circular region is sharper here compared to this? Definitely yes. At least on my laptop screen it is very clear. So please observe these images, sometime you will see that. So the concept is, to the original image I will be adding the Laplacian. Okay, now you may be seeing that a negative sign here. This negative sign is only because you want to take care of this negative sign, that's all. Okay, so when the center coefficient is negative, just do a minus sign. So because when I do a minus, this will become plus, so it is as if I am adding. Okay, so don't think that I am subtracting, it is actually addition only. If the center coefficient is positive, if it is positive here, when I take when I add directly, it will do it. Okay, so if the center coefficient is negative, you just do minus of that, which means this operation is addition. Don't look at this operation as subtraction. I hope you understood. Okay, so what I am trying to do, to the Laplacian I am adding original. That's what I did. I took the Laplacian of an image and added to the original. Okay, now you already have seen the equation for Laplacian. Okay, and if I just do addition, for example, if the center pixel is negative, I should actually add it with minus 4, minus f of x comma y. So minus 4 plus minus 1, I'll get it as minus y. Okay, uh, and if it is okay, multiplied with a minus sign, I'll get plus y. So that is how I'll get this. So the only difference between this and Laplacian is, in this case, edges are very clearly visible along with the smooth region. In Laplacian, you will only see the edges. Okay, that's the difference between this image and this image. This is only the Laplacian, that means only the edge information is visible here. When I add this to this, I'll get the same image except that the edges are crispened. So you can probably apply this type of filter on a license plate image and try to improve the edge information so that your character recognition would be better. Okay, is the point clear? What is edge crispening? Just add original to the Laplacian. Okay, I again repeat, don't look at it as subtraction, you are adding. So I am just adding original to the Laplacian, that's all I am doing. So I am getting a edge crispened image. So I think there is an example image given here. So you can observe that the center pixel is plus 5 now. Okay, others are minus 1. If suppose if I also consider the diagonal neighbors, the center pixel is plus 9 and others are minus 1. So this is a Laplacian mask. This is in fact an image on which you are applying these two, and just see the results. Hopefully you can compare these results you can clearly see this area. It is very sharp here. Hope it is very clear. Okay, so that way I can sharpen the edges of an image and use it for further application. Okay, so yeah, I think we still have time. Let us continue. Now, a variant of this filter is what is known as unsharp masking, and of course, a small change. It is we can also have what is known as high boost filtering. Again, the concept is very simple. See what we did here. To the Laplacian, we added the original. I repeat, to the Laplacian, we added the original. So we got a sharpened image. We are doing a slightly different thing here. You subtract the blurred version of the image from the original. Subtract the blurred version of the image from the original. Okay, then we call that as unsharp masking. I repeat, the blurred version should be subtracted from the original. Okay, instead of just uh, doing that, suppose if I just okay scale this value and add it to the original, then we call it as high boost filtering. So observe here, suppose if k is equal to 1, what I am trying to do is to the original I am just adding this. Okay, that means the uh, subtracted blurred image from the original. Suppose if k is greater than 1, you are just scaling this by some amount and adding it to the original. Okay, and in fact this is demonstrated by using a very simple one-dimensional image signal. Let us assume that you have a original signal of this nature. That means the value is constant here. There is a ramp edge here and it becomes constant. Now when I blur this, obviously you know that these type of sharp edges are smoothened. So you would see that blurring happening here. Okay. Now when I subtract this blurred version from the original, that means I should subtract this from this. Obviously this minus this is 0. This minus this is 0. So you would see that only near this edge information you will have the unsharp. Okay, you will have that value because you have subtracted the blurred value from the original. So obviously wherever it is constant it is 0. Now if I add this to the original, if I add this to the original, this is what you notice. So you can observe that smooth region remains as it is, whereas the edges are sharpened. Observe that because the edges are sharpened. So this is called unsharp masking. And instead of just adding the original to this, if I just scale this by amount and add it, then we call it as high boost filter. Okay, so I think the concept is clear now, and probably the okay. I think we are almost yeah. I think there is an example. Let us see that also. This is a original image of size 600 cross 259 pixels. Then you have blurred it by using a simple 31 cross 31, a Gaussian type of low pass filter. We'll discuss about it in the end later in the next class maybe with some variants. Then the third one is a mask. That means you just subtract this from this. So this is what you get. The fourth one is unsharp masking. That means I'll add this to this. This is what. So hopefully you could compare these two. This is much sharper compared to this. That's what has happened. It has become sharper. Now in the second case, you have taken the constant k is equal to 4.5. So you could observe that the image is still brighter because the smooth region is also multiplied with a constant. That is why it is looking still brighter. Okay, so this is how actually we can just use unsharp masking to improve the sharpness of the image. Okay, so with this I think there are two more slides to be discussed before we go to the next topic. Hopefully we will do it in the next class because it's need some more explanation, so I'll probably close now.